So, my name is Luis Felipe Longo, and I have been working in CBPF, Rio de Janeiro. It's the Brazilian Center of Physical Research with my advisor, Mark Casals. And I'll be talking about my work that is basically a new approach to calculate quasi-normal modes in KERR spacetime. So first, what are and why should I care about quasi-normal modes? Most of you probably are familiarized with normal modes as the leading frequencies in the ring-down waveform, but they can tell us a lot more of the black hole spacetime. For instance, they can say about the mode stability of the black hole. For instance, if the quasi-normal mode that has a positive imaginary part, the mode would have exponential growth with the time, so would lead to an instability of the black hole. The quasi-normal modes are important as well for the modeling of MRAs, the stream mass ratios in spirals. And there have been some conjectures about quantum properties in black holes with the quasi-normal modes as well. So the quasi-normal modes appear in black hole perturbation theory. And in our case, we use the background metric as a KERR metric. And we use to calculate perturbations as small particles going into the black hole. For instance, the stream mass ratios. And, of course, in the ring-down phase. The limitation of this theory is to stay in where the perturbations are not so big. So, for instance, I said that some quasi-normal modes can lead to instabilities, but at some stage, if you have this positive imaginary part of the quasi-normal mode, the numerical relativity would go into place, so would have a different theory there. So the goal was to achieve a master equation for the field perturbation in this space-time, and this was achieved by TEUKOLSKY in 1973. And what he did, he went to the Newman-Penrose formalism, choosing a null tetrade basis, and compute the various scalars of this metric. For instance, psi 2 in the KERR metric is the only one that is non-zero. So all the other quantities are perturbative quantities there. So this is a weird quantity to compute, but if you go to large distance, you can see that psi 4 is basically derivatives of your H cross and H plus. So he was able to get to a differential equation for psi 4. And with this ansatz, he gets the angular part given by a spin-weighted spheroidal harmonics, and the radial part would be driven by this equation. And the point is how to solve it. And that's where the MST method comes into place. So what we need to solve a differential equation, for instance, a second-order linear differential equation, we need two linear independent solutions that is R in and R up in our case. And we can construct the green function with them in the usual way. This green function would be able to evolve any initial data to get the waveform in the ring-down phase. When I say any, it's any inside the linear perturbation theory. So what is the, mathematically speaking, what is the quasi-normal modes? They are defined with no outgoing wave in the horizon and no incoming wave from the infinity. So they are free driven oscillations. There is no external force there. And in a more mathematical definition, they are poles in this green function. Why they are poles, you can see that when you will evolve get the waveform, you will integrate the green function against the source. Sorry. In R and in omega. And if you go to the integration in omega, in the complex plane, you are going to these regions here. And by the residues theorem, you will get the poles in this, the residues in this complex plane. So that's how I'm going to compute the quasi-normal modes, by looking to these poles. And these poles will happen when the Wronskian is 0. And the connection between this mathematical and the physical sense is that the Wronskian can be proven to be proportional to the incident wave amplitude. So this has to be 0 as the definition of quasi-normal modes, and put in here would be poles in the Green function. So what is the MST method? This is a little bit more technical, but we get two solutions in the horizon, near the horizon and near the infinity. And you propose basically ansatz that encounter for these asymptotics regimes. And what happens is that in the horizon you get a solution as series of hypergeometric functions, and in the outer solution you get series of Coulomb wave functions. In the between, you will encounter this parameter nu, that is a renormalized angular momentum, that has to be carefully chosen to give the convergence of this series. This parameter happens in the two solutions. This solution here would be convergent for any finite r, and this one would be to all r except in the horizon. So now what we need to do is to match these solutions, and with this matching, we can find the asymptotic amplitudes for the two solutions of the TEUKOLSKY equation, the in solution and the up solution. When we do that, we can compute all the amplitudes, for instance, the incident wave and the transmitted wave of the in mode and the up mode. And with this, compute the Wronskian and look for the zeros there. So these are the results. So this is for Schwarzschild, Schwarzschild spacetime. We can see some properties. This is for spin 1, so electromagnetic field perturbation and gravitational field perturbations here. They all look symmetric around the imaginary axis, and this should be the case because the only way to give rise to a real perturbation is that if you excite complex conjugate modes at the same time. For the electromagnetic spectrum, there is no algebraically special point. That is this point here for the gravitational perturbations. And what is good about this method now is that this point can be calculated analytically, and this is the solution. But the previous method that was done in the literature couldn't quite find the exact value. It was close, but not the exact one. And this is probably because in this region of the complex plane, there is a branch cut in the function. So it would be hard to analyze there. In the 2000s, Van der Brick, I think that is his Deutsch, he said that this was probably a numerical error in the previous method. It's this one point here that there is no imaginary part. No imaginary part. No real part, sorry. The same guy, Van der Brick, he said something about being the totally transmitted mode. So I can point it to his work to have the argument, but I'm not 100% sure of the interpretation. Yes. Okay, so the next part was going to near stream of KERR. What happens there is quite interesting because Bertie pointed out in this paper that there is a branching of your spectrum. So for instance, there is two branches of the quasi-normal modes for some modes. For instance, if this parameter, this mu parameter here, that is a relation between M and L, it's larger than a critical value, 0.74, you only have one branch. And if it's smaller, you have two branches here, a principal one and a secondary one. The principal they call zero damping modes because they are accumulating to a point that has no imaginary part. And the damping modes because they do not go to a zero imaginary part as A go to the extremal value. So in here, we can see no damping modes, and here we can see damping modes agreeing with this paper by Bertie. So here is just to point out the accumulation of the points. So here the Schwarzschild case, and here is the near extremal KERR case. If I zoom in into the first 10 modes, we can see by the imaginary axis the accumulations in this point. So what happens is that they are accumulating in this point that is actually the superradian bound frequency. That is the limit of whether you can have superradiance in your KERR black hole. So from the paper by Bertie, we can see that approximate relations to the zero damping modes. And what is happening here is that you have a roughly constant real part and a change in the imaginary part by a fixed amount, depending on this, on the value of A. Delta here is just a function that is roughly constant as well, but it depends on Lm and the eigenvalue of the spin-weighted spheroidal harmonics. So conclusions. Oh, just one thing. In the extremal KERR case, these points will accumulate there, and we want the idea is to investigate there because the method already has been proven to be good enough to look near branch cuts. So the conclusions, we were always, our findings were always consistent with the previous methods, with the advantage of finding the quasi-normal mode in the branch cut. And the downside of the method is that for large frequencies, the method is really slow because the MST method is well adapted for small omegas. And now we are going to the stream KERR case to see what is happening in the superradian bound frequency. So thank you.